Swayam Prabha. Digital India. Educated India.
When two random variables are independent, I am going to give it as one important result as a theorem. Let x and y be a independent random variables, and g and h be Borel measurable functions, then we will conclude after we get the result. So, let me keep the then word as it is. Let us go for finding out what is the probability of g of x less than or equal to x with h of y less than or equal to y. Let us go for finding out a function of a random variable with x in the form of g of x, function of a random variable with the random variable y in the form of h of y. We will try to find out the joint CDF of the random variable g of x and h of y. Since x is a random variable, g is a Borel measurable function, therefore g of x is a random variable. So, you can think of g of x is some other random variable. Similarly, y is a random variable, h is a Borel measurable function, therefore h of y is also a random variable. So, you can think of some other random variable. That means you can treat g of x is another random variable, third random variable other than x and y, h of y is a fourth random variable. We are trying to find out what is the joint CDF of these two random variable, whether that satisfies the independent condition. If they are going to satisfy the independent condition, then you can conclude g of x and h of y are also independent random variable. That is probability of x belonging to g inverse of minus infinity to x closed interval, and since h of y is less than or equal to small y, this also can be written y belonging to h inverse of minus infinity to small y closed interval. That is same as the probability of the way we write x belonging to g inverse, y belonging to h inverse. We know that the random variable x and y are independent. Since x and y are independent, x belonging to some Borel set, y belonging to some Borel set, the probability of that is same as probability of x belonging to the Borel set, that is g inverse of minus infinity to small x. Similarly, the product of probability of y belonging to h inverse of minus infinity to small y, because x and y are independent. That is same as the probability of g of x is less than or equal to small x multiplied by probability of h of capital Y less than or equal to small y. and this is valid for all x and y. This is valid for all x comma y. That means the probability of joint CDF is same as the probability of g of x and probability of h of y less than or equal to x and less than or equal to y respectively. Since this condition is satisfied, we can conclude the random variables g of x and h of y are independent random variables. This is a very important result. Whenever you have an independent random variable, if you create a Borel measurable functions on those independent random variable, that is also going to be a independent random variables. As an example, we can think of already we discussed 3 examples. So, the fourth example is let x and y be independent random variables. Define z that is equal to x square, w is equal to mod y. That means I am creating a g of x as the x square and h of y as the mod y. And since these two are Borel measurable functions, g of x and h of y form, we can conclude z and w are also independent random variables. Since x and y are independent random variable, z is a Borel measurable function of x, w is a Borel measurable function of y. Therefore, z and w are also independent random variable. The next concept which we are going to discuss as the form of definition, that is IID random variables. We say that xn is a sequence of independent, identically distributed random variables with common distribution if the sequence xn is an independent sequence of random variables and the distribution of each random variable xn are the same. Whenever we say the sequence of random variables are IID, that means the first I comes from here, the second I comes from here, the D comes from here. Whenever we say the collection of random variable or the sequence of random variables are IID, that means they are mutually independent as well as the distributions are same. Whenever the distributions of few random variables are same as well as all those random variables are mutually independent, then we can conclude that collection of random variables are the IID random variables. We can go for creating a simple example of IID random variables. So this is example number 5. Let x and y be a continuous type random variables with joint probability density function is given by e power minus x plus y, when x is lies between 0 to infinity and y is also lies between 0 to infinity, 0 otherwise. We started with the two-dimensional continuous type random variables with the joint probability density function, that is e power minus x plus y within bracket, when x lies between 0 to infinity, y between 0 to infinity. You can verify whether this is going to be the joint probability density function by integrating joint probability density function with respect to x and y, that is same as 0 to infinity e power minus x plus y dx dy, that is same as 1. Therefore, this is a joint probability density function. Let us go for finding out the marginal distribution by integrating the joint probability density function with respect to y, that is 0 to infinity e power minus x plus y integration with respect to y. If you do this integration, you will get the answer, that is e power minus x when x is lies between 0 to infinity. So this is the probability density function of x. Similarly, if you do the exercise of finding the probability density function of y, you will get e power minus y when y is lies between 0 to infinity, otherwise it is 0. If you cross check the joint probability density function, whether that is same as a product of probability density function of x and y for all x and y, the joint probability density function is e power minus x plus y, and the probability density function of x is e power minus x, probability density function of y is e power minus y. So this condition is true for all x comma y. Therefore, we can conclude x and y are independent random variables. Not only that, the probability density function of x is e power minus x, probability density function of y is e power minus y. So if you find the distribution, that means the CDF or probability density function for a continuous type or probability mass function for a discrete type, the distributions are same. The distributions of x and y are same. Also, they are independent random variable. Therefore, we can conclude the distribution of x and y are same, or the same. We can conclude in notation, we can use x is capital Y in distribution. They are identical distribution. The distribution of x and the distribution of y are same. We can use the word D above the equal symbol, that means both are having the identical distribution, and also they are independent. Therefore, we can conclude x and y or IID random variables. So whenever we write IID random variables, that means those random variables are mutually independent. Also, they are having the same distribution. Then we call it as a IID random variable.